Hi everyone and welcome to the course named Digital Design with Verilog. So this will be the first module, okay? Then there will be second module. I hope you have watched the introduction video and the roadmap and the course curriculum, all those things I've explained in the introduction video. So make sure you watch that video and there I have discussed about the syllabus. So today we will start with the module 1 with the lecture 0 where I will introduce you to Verilog, why Verilog is required, and like what is the bigger picture in digital design, what are we doing. Okay, so obviously we will not discuss about coding in the first few lectures, like 1-2 lectures. Then I will come to the coding. Before that we have to make a groundwork, make a foundation, the reasoning behind the need of Verilog. Then obviously we'll go to coding, and trust me, whatever you will learn, right, you will learn everything crystal clear, and everything, reasoning for everything will be clear to you. So let's first discuss about the evolution of digital design. So digital design is the process of creating electronics primarily using digital circuits. Okay, what are digital circuits? Like zeros and one, right, which operate on 0 and 1, just like your computer, your mobile, everything, any electronic component works on zeros and ones. Okay, it focuses on designing systems such as processor, memory units, and communication systems. Okay, so like I hope this is a very famous picture. I think this is from the Bell Laboratories, where like they were building some supercomputer, like which was not able to process much, but the computer was so much bulkier. I think it was around 1960s or something like that. But today, if I show you something, if any of you guys have are tech enthusiasts, or if you know about Apple, so like this is a few years back they released their chip named M2, Apple M2, right? In M2, previously, right, we had so many bulky things. Everything was separate. RAM was separate, processor was separate, storage was separate, then IO was separate. Everything was separate. This M2, right, M2 chip which Apple actually built, it had everything inside it. It follows the ARM architecture. Don't worry if you don't know these technical terms. That's totally fine. For the students who know this, I'm just explaining you because the interest may be more risen due to this fact, right? This M2 chip, okay, this is the Apple silicon. Inside it we have 15.8, like it can do 15.8 operations per second. Okay, it has 24 gigabytes of RAM, like it is very small. Okay, it has 20 billion transistor. That is the most important fact that is interest to us, because we design anything with transistors, right? In an electronics domain, we design anything with transistors. So it has 20 billion transistors. Now, of course, you are not mad. I am also not mad. How can I design anything with 20 billion transistors? There has to be a method. There has to be an automation tool. So exactly, Verilog also is a one of the small thing that comes in the whole design flow for the automation. Obviously, we cannot design anything with 20 billion transistor, right? Of course we can design, but manually we cannot. There needs to be a automation tool, because if we go into transistor level and place each transistor by hand, okay, then we have to take care of the like saturation levels, okay, whether the transistor is operating properly on active region or not. Okay, so we have to take account of all of that, but there has to be automation tool that we'll discuss. So that is what we do. We make few abstractions, okay, because initially what we used to do around 1978, we used to design our circuit with transistors. We just placed a PMOS and MOS, like that we used to design our circuit. Then we move to schematic entry. I will show you, I will tell you about each level slowly. So the transistor level, which is here, is the lowest level, dealing with individual transistors and connections. So their gate drain connections, source connections, all those things individually we connect. This was around 1980s. After 1980s, we moved to gate level abstraction, design abstraction, where we used to design our circuit with logical gates. We inside logical gates, of course, there are transistors. A AND gate will be made with CMOS transistors, and OR gate, anything. I hope you know all this. So, but we didn't used to uh, take care of the individual transistor level connections. We just used to take care of the gate level connections, like AND gate output will be connected to the next circuit wire, okay, like that. This was in the schematic entry. That was also a bit on the higher level. So then we move to register transistor level. What is register transistor level? Register transistor level focuses on data transfer between registers and functional blocks using hardware. Okay, so registers are actually on the higher level. Registers are made with gates as well and with few sequential blocks as well. Okay, so then we what we do is we define the next cycle value depending on the current state. So this, right, used to use the sequential logic. Previously we used to build everything with current logic, like this AND gates, right? They don't have any cycle, they don't have any sequential logic to them, right? I cannot define a next state equation. If you have studied digital electronics, you will understand this. So these gate level, right, only are used to design the circuit depending on the current state. Okay, but these, right, RTL, we can design the circuit depending on the current state and on the next state. That was the most important thing. Okay, and transistor levels, what we do, like basically in transistor level, right, we have to decide whether the next transistor will be on or off in that particular state, right? But that is very tedious for us to decide. That's why we moved on to this, and then we moved on to the higher level of abstraction. Okay, so this register transistor level focuses on data transfer between registers and functional blocks using hardware description languages like Verilog or VHDL. So this RTL is where we will code. Like this is the abstraction that we will do, right? Because it has a very good blend of hardware and software. Okay, so we will use hardwares which can actually we will design logic depending on the current state and the next state, and those hardwares will then talk with the transistor. That is a other thing that we don't take care. We don't take care of the transistor, we don't take care of the gates. We just decide what type of registers to place. And obviously registers is not only register, there are many things as well which I will discuss, don't worry about it. But for now, just understand that we will code our whatever we do, right? We will be in this level, register transfer level. Okay, then the next level comes, that is even higher level of abstraction. As I move down, right, the level of abstraction becomes higher. Now why does the level of abstraction become higher? Because the more lower, like the more higher level of abstractions you go, right, the more further away you move from the hardware. So sometimes there needs to be a good balance, because of course you want to have a control over the hardware as well, what type of hardware you want to use. If you automate everything, then maybe the CPU has chosen a optimized hardware, but maybe that is not properly optimized. Okay, then you have to decide what kind of hardware to choose. Yeah, sorry for the noise. So in gate level modeling, right, so not modeling, gate level abstraction, we actually cannot store values and all those things. In register level abstraction, we can store values. Like if you have studied COA from me, then you might remember there is a, like if I do write something like this, right, R3 is R2 minus R1. That means what? I'm taking values from R2, taking values from R1, subtracting the two, and then storing it in R3. So this is what we do in register level abstraction, and that is why storage is very important. We will understand this slowly. Then what is system level? Like system level is which combines the complete system, and we don't code here in Verilog. We don't do system level. What is system level? We don't take care of the hardware at all. Like C++ and Python, whenever you code in C++ or Python, do you consider, okay, I am writing A equals to B plus C, which kind of hardware will it use? No. In Verilog, you have to think about that. If I write A equals to B plus C, then maybe it will implement a adder as a hardware, okay, in Verilog. But in C and Python, right, we don't think about that. We just write A equals to B plus C. That's it. Okay, we don't think about the hardware. So it is just on the highest level of abstraction. It is further away on the hardware. Okay. So we will use RTL because what it does is it is a bridge between the hardware and the software. So it glues the hardware and the software together, and we need to have both. We need to have a control over both. Of course, as I mentioned, 20 billion transistors are there. I cannot control each transistor. Okay, 20 billion transistor. That's why some level of automation needs to be there, but some level of control also needs to be there to the hardware. So that's why we use the Verilog. Verilog is a glue between hardware and software. Of course, there are many components between hardware and software. One of those components is Verilog. Okay, there are other components which I will not discuss here. That is not in our syllabus as well for now. Okay, so basically, what the programmers do, programmers code in C++. If you remember, the C guys, coding guys, they code in C++. But someone in C++ also, what we do, someone in C++ needs to convert to machine language. Because if you have, like, even if you have done some basic programming, right, you know that when you write a code in C++, okay, language, when you write a code in C++, like int I, now if you tell this to CPU, will CPU understand? No, CPU just understands zeros and ones, right? CPU just understands zeros and ones. So of course someone needs to convert it. Who converts? Assembler. If you remember, compiler or assembler or something like that. Okay, compiler, like, both have different tasks, but for now I'll just make them together because this is not the purpose, just I'm explaining you. So similarly, in coding domain they have some converter, right? In our digital domain also we have some converter, because we, of course, if we, like, let's say I want to design a counter, okay, I will not directly design it hardware, right? That will be so much tedious. What I will write, I will write a code, okay, of a counter. I will write a code of counter. I will not explain the logic right now, okay, and that logic will be automatically synthesized to a hardware, which we know, okay. So that level of automation we need to make. So for that level, right, we do RTL coding, register transistor level. So we do RTL coding of a counter, then our synthesis tool, right, synthesis tool converts this into hardware, okay. So that is what we mean by synthesis tool. Now there are many types of synthesis tool. If our RTL, if our this RTL coding, right, is converted to gate level of abstraction, okay, then it is known as logic synthesis. Why logic synthesis? Because gate is combinational logic, right? You are telling the combination logic, that's why it is logic synthesis, okay. This is what our Verilog will do. Verilog will do logic synthesis. It will just convert your RTL code into gate level of abstraction. Now what does, if I directly want to convert RTL code to transistor level of abstraction, that is very difficult to do, transistor level of abstraction, then this is known as physical synthesis. Physical synthesis. Now we have tools for this, which of course we will not discuss mainly. So in Verilog, what we do, this is the most important portion. Okay, sorry. In Verilog, what we do, in Verilog we do this, we do logic synthesis. So in logic synthesis, basically we convert our RTL, that is register transistor level code, it has a logic, okay, RTL to our gate level of abstraction. That is what Verilog will do. It is a synthesizing tool. We will write our code in RTL and Verilog will automatically synthesize in gate level of abstractions. So let's come to the automation tool. As I was discussing, we have 20 billion transistors, we have to automate few things. So there came few automation tools, electronic design automation, also known as EDA tools. EDA tools automate the design, simulation and testing of electronic circuits, making the design process faster and less error prone. If human is involved, you know, error will be there. So we will try to make our process as smooth and fast and error prone as possible, okay, less error prone as possible. Now what happened, initial days we used to do manual design and test with breadboards. If you have done bit of lab, you will know what breadboards are. We used to test those manually. But after few days, we came to the gate level design as shown in the gate level abstraction. In gate level abstraction, we introduce CAD tools for schematic capture, like Cadence. In Cadence, right, we can have a block okay, like an AND gate or something, and that is used for schematic capture. Previously we used to do manual entry, okay, manual drawing the blocks and all those things. That is very tedious. Next we came to RTL design. Okay, what RTL design did, it used hardware descriptive languages such as Verilog and VHDL for design specification. We didn't have to use cadence. We just directly coded our design. Let's say I want to build a counter, I just directly coded a counter, and in Verilog and few languages such as hardware descriptive languages. So this Verilog and VHDL are known as hardware descriptive languages. We'll study Verilog obviously. What does these languages do? This convert our logic, that is our RTL code, to hardware. So it became simpler. Before it was like I have to make a design entry, although everything is not properly seen with the picture. That's why we code it. Seeing the code and understanding the code is easier. Okay, so code gets converted into hardware. That is much easier for us. Yeah, sorry for the interruption. There is too much background noise. Sometimes I have to cut the videos. So as I was explaining, what is SoC, system on chip? So this Apple, right, Apple M2 silicon, whatever you've seen, it is SoC. So what we do, we implement multiple functionalities in a single chip. Just like in this M2, right, it has a RAM, it has a VRAM as well, it has GPU, CPU cores, everything it has inside in this one single chip. Okay, that's why it is called as system on chip. So I hope you have understood this thing. Like now we do these kind of designs. Currently what our advancement is, we have so good automation tools, we can implement all those things in a single chip. It helps. Why it helps? Because if everything is in a single chip, right, then there is no delay between the data transfer. The GPU or CPU can directly transfer data very fast manner. So that's why we want to build everything uniformly in a single chip. Okay, there are many more advantages which of course is out of the scope of this course, so I will not discuss about that. So of course, like I will tell you basic things about digital circuits. I hope you have already studied digital electronics from us. Okay, so what does digital circuits do? Digital circuits basically manipulate the binary data 0 or 1 using the high voltage and low voltage levels. Very simple, right? Only two voltage levels we have, 0 and 1. They perform computations and make logical decisions based on the inputs. So if I'm giving some, if I have a OR gate, if I am giving it 1 input, right, output will be 1. If I have a NOR gate, if I'm giving 1 input, output will be 0. So like this. So that is what digital circuits work. So this is digital circuits. Now what are combination circuits? So combination circuits produce outputs based solely on their current inputs, and they do not retain any past states. Okay, just take an example of few combination blocks like adders, multiplexers, decoders, encoders. These are all what? These are all gate level abstractions. Okay, they don't take care of the previous state, just they take care of the current state. If you have studied sequential digital electronics from us, you will understand the difference. Okay, so these are few examples, and what we do is we define the desired output, what output we need to get. We use the truth table to establish the relationship between the inputs and the outputs. Then we simplify using the Boolean algebra or K-map. Okay, so this, right, whenever we do these kind of things, we use gate level of modeling that I will explain later on. Don't worry about it, but this basic thing you know obviously about combinational circuits. In sequential circuits, what we do, we have, like, we can store information as well. Sequential circuits have memory elements, so this comes to the RTL level of abstraction, meaning the desired outputs depend on both the current inputs and previous states. Because it has memory elements, so it can store the previous states, and obviously current input will be given from the input itself, so the output will depend on the current input and the previous outputs. Okay, previous input, sorry. What are the components of a sequential circuit? It has flip-flops like T flip-flop, JK, SR flip-flop, registers, counters. Okay, what is the working mechanism? Working mechanism is simple. Like, it will have some clock signal which synchronizes and the state changes. It will have a feedback loop, obviously that feedbacks the previous values, okay, to retain the past values. What are the applications? Memory systems, control units, communication protocols, etc. There are tens, hundreds, thousands, billions of applications. Everything uses sequential circuits. Okay, So like this was just a block diagram, this is just example. These things you know, that's why I'm not giving too much emphasis on this. You already know about this because you have already studied the digital electronics formers. The third one is again an interesting thing, that is FSM. Of course, don't worry, we'll code all these three. We'll code all these three, okay? What is FSM? FSM are mathematical model used to design sequential circuits. They help in managing complex state transitions. Like if currently I'm at a present state, depending on the input and the present state, maybe I will go to this state or other state. There can be multiple states, okay? So that is what FSM does. I hope you have learned this. So basically what we do, we have to code. Our code will depend, right? Our code will depend on the on few specific condition, okay? Next state will depend on specific conditions. Like if I am at this position, then the next state will be this. If I'm at this position, then the next state will be this, okay? So don't worry, we will code all these things. You don't have to worry about this at all. But just giving you an overview, what circuits we'll design. First we'll design combinational blocks, then we'll design sequential blocks, then we'll design finite state machines, okay? So what are the components of a FSM? First is states, represent the various condition of the system. Let's say let's say human, right? I can be hungry, I can be sleepy, I can be lazy or something like that. My current state is I'm hungry because I haven't ate for 6 hours. That's why I'm very hungry. So depending on the previous state, because I haven't ate for many hours, I'm hungry, okay? So that can be a state. Okay, then transitions. So if I'm hungry, then what I will do, I will eat the food. I will take a food from the fridge and I will eat the food. So transition is I'm going to the fridge and taking out the food. I'm going to the fridge and taking out the food. What is the output? Output logic is I'm eating the food, something like that, okay? Just giving you an example. Don't worry, we'll do this FSM at the end. This will be at the module 2, okay? So example of a FSM is a vending machine. Its states can be ideal, accepting coin, or dispensing item. So like if a vending machine is there, if you know about vending machine, you can put, like you can first press what you want. Like I want a cold drink or a milk, I will press that with the buttons. Then the vending machine will show that input 10 rupees. So I will input the 10 rupees and then the vending machine will open the door and automatically give out the object, okay? So that is what we do here as well. So like it has three states. Either it will be idle, nothing is getting done, or it is in the state where it will accept the coin, or it is in the state for dispensing the items, okay? Like basically giving out this milk. So transitions based on the coin input and the item selected. If I give it a 10 rupees coin, then obviously it will give milk carton. If I give it a 20 rupees, like if I purchase a 20 rupees item, then it will give out a 20 rupees item. That is the transition. And dispense output is the dispense out item or return change. Because let's say I want this milk. Milk is 10 rupees. I have given it 20 rupees. So vending machine is smart. So it will give out the milk and it will give out the change as well, because I have given it extra 10 rupees. So it will give out the change of 10 rupees. So it will be total like it will give out 10 rupees as well as a return and the milk carton as well, okay? So these are the few states, okay? So basically these are the few things that we will do with RTL coding. RTL coding is much more deeper, because basically right here in RTL coding like this, right, this is also done with the sequential logic only, because sequential logic also has some storage and all those things. So this can be done with sequential logic. So RTL coding, right, this is what combinational circuits is. What, like data is here xy, it is flowing throughout this path and getting to the output, okay? There is no storage or something. So this kind of circuits are also known as data path circuits, because I'm giving some input here and the data is propagating to the output, okay? Now next is here as well. I'm giving it some input and at the end I'm getting some output through the path. Of course, I'm taking into account the initial previous states as well, okay? So this is also known as data path. And this FSM, right, is actually known as a controller, Why controller? Because it has a lot of logics depending on the current state, depending on its states, output, input, all those things. It has lot of logic. So FSM has a lot of logic. So what we say is that's why it is a controller, because it controls, right? It controls the state, input, output, logic, transition, all those things. That's why it is a bit complex. Don't worry, we'll discuss about this in the last few chapters. So basically what I want to come to the conclusion is that RTL coding, right, has everything. RTL coding has data path as well plus controller. It has everything, okay, but it is not important for you. Just telling you an overview what is RTL coding. This will, when you will go to a job, right, there you will understand about RTL coding more. For now, just understand basics of Verilog, that's it, nothing else. You don't need to understand anything else. Just wanted to give you overview that RTL coding involves combinational blocks, sequential blocks, and FSM. Only these three blocks, these three types of blocks we have. Except this, right, we don't have anything else, okay. So this is actually not that important. This page I can remove. Okay, so now let's come to the a bit of VLSI domain. So what is VLSI domain? I already have explained about digital circuits. So let's understand the development of VLSI domain. VLSI is what? Very large scale integration. Refers to the process of creating integrated circuits, ICs, by combining thousands to millions of transistors onto a single chip, like as shown in the example of Apple M2 chip. There are billions of transistors inside. So obviously we have developed VLSI. First it was microprocessor, then we developed memory chips, now it is system on chips, okay. It is more efficient. So we started with SSI. What is SSI? It is small scale integration, whose year is 1964. Previously, like, these are the like stats, transistors per chip, logic gates per chip, it is very lower, okay. Then we came to medium scale integration, which came into account, like the year can be roughly wrong, but around this time only it came in 1968, whose which has transistor per chip a bit higher than the previous case, if you see. Then the logic gate per chip also increased, right? And of course we developed few complex circuits like multiplexers, decoders, counters. Next we came to large scale integration, which was developed in 1971, where transistors per chip were increased even more. Like you can see, like the development is 20 times more, something like that, 20 to 40 times more. Logic gates per chips also increased, and we developed microprocessors around this time. Then we came to very large scale integration, VLSI, which we got to know today, like which we currently are using, and obviously we have moved to this as well, but we use this one as well, okay, which was founded in 1980. The transistor per chip raised to a very high level, logic gates also raised, and we developed advanced microprocessors, memory chips, and ASICs. What is ASIC? ASIC is application specific chip, or application specific integrated circuit IC. Application specific ICs. That is what we mean by ASICs, okay. So like we will come to this as well. I will explain you a bit of ASICs, because knowing ASICs is also important, because few companies hire ASIC engineers. You have to know what is ASIC actually, so I will tell you about that as well. Then we came to ultra large scale integration, which are like this is the architecture which our modern CPUs, GPUs, all those things use, like the Apple M2, right? So you can see the stats. So this is a bit about the VLSI domain. Now I will discuss about CMOS, complementary MOS metal oxide transistor, okay. Because you already know about CMOS, because you have studied digital electronics from us. Why we use CMOS? What is the reason for using CMOS? CMOS is a widely used technology for designing integrated circuits, that is also known as ICs, due to its low power consumption, high performance, high integration capabilities. It can be integrated with other circuits, okay. That's why. So that's why we use CMOS. CMOS circuits are a combination of p-type and n-type MOSFETs. P-type is at the top, PMOS, and NMOS is at the bottom. Generally it is symmetrical, right? CMOS circuit is symmetrical about the middle, basically. I cannot say, basically in the bottom we'll have all NMOS, in the top I'll have all PMOS, to implement logic functions. So like one by one I will go through the advantages of a CMOS. First advantage is very obvious, it has low power consumption. Why? CMOS circuits consume only power only during switching and almost no power in a static state when inputs and outputs are stable. Why it only consumes power only switching? First of all, let me say why it does not consume any power when it is in the static state. When it is in the static state, right, we know our gate current Ig, right, is almost very low, almost equal to zero. So to turn on or off the device, right, basically I have to apply some voltage here, right? So as the gate current is very low, Vg will be some finite value, Vg into 0 will be 0, right? So then the power is 0. That's why it has no power. But while turning it on, obviously there will be some transient, there is some MOS cap and something like that, some current will flow, okay? So during switching there will be some current, but in stable states there will not be any current at all. So Ig is 0, right? That's why it has no current. So this property makes CMOS ideal for battery powered devices like smartphones and laptops, because we have power constraints on laptops and smartphones, right? Because battery capacity is limited. That's why. Next reason is the fully restored logic levels. CMOS ensures that the output voltage levels are fully restored to the supply voltage levels. Okay, what do I mean by this? So if there is logic 1, right, it will pull up to high plus VDD and fully restored logic levels. If it is logic 0, it will pull down to ground. But few other circuits, right, they always don't do this, they always don't behave like this, they always don't restore full logic levels. They will not go to plus 5 volts or 0 volts. They can be, sometimes they can vary, right? Sometimes they will go plus 7 volts for high I'm talking, plus 8 volts, plus 0.6 volts, something like that. And for low as well, sometimes they will go 0.4, 0.3, it may happen. So they are really not that ideal to use, because they are not going too much 0 or too much 1, right? We need fully restored levels, because in digital what we do, mainly in digital we only use zeros and ones. To identify zeros and ones better, we have to have either very high value or very low value, because even if there is signal degradation, it ensures reliable operation, right? That is what is written in the last line. Even if there is some signal issue, right, still I am able to identify that it will be high or low. That is what we need to do. Okay, next come to this CMOS, complementary metal oxide semiconductor. uh, Sorry, this is the full form basically. Third point is on off times are similar. So as it is symmetric, right, the on off times will be almost similar. There will be bit of difference, but we will design our PMOS and NMOS such that the on off times are similar. Why? Because when you turn on, right, when you turn it on, when you make it high, then what happens? Then actually, sorry, when you make it high, right, then NMOS turns on. NMOS turns on, right? I hope you know basic MOS, CMOS. So if NMOS turns on, so this output Z will be pulled down due to the NMOS. So the pull down is happening due to the NMOS, and when this X is 0, the PMOS turns on. If the PMOS turns on, the pull up happens due to the PMOS. Okay, so I will say pull down due to NMOS and pull up due to PMOS. Okay, pull down pull up happens due to PMOS and NMOS. Now what you have to identify is that they are two different. So if they have different switching characteristics, obviously it is pulling it down, right? There will be some time delay. So if the two different transistors are not balanced properly, there will be different, like pull down time. So initially it was, let's say, high. Okay, initially let's say it was high, then it took this much amount of time t1 to pull it down, right? Let's say initially it was low, it took this much amount of time t2 to pull it up. So if t1 and t2 are not same, right, there will be problems. If obviously we want everything through symmetry, and I will not go to everything like in detail, but we need similar rise time and fall time. So rise time and fall time should be same. So what we do, I will write here. So as to make rise time and fall time same, we adjust our height, W by L ratio. Okay, we cannot adjust L, actually we don't have like control over the L, but we will adjust the width of PMOS and NMOS. Okay, so to make it symmetrical, so although they are almost symmetrical, but we can adjust, we have the control to adjust over the rise and fall time. Okay, that's why this is very good. Then high integration capacity, high integration capability. CMOS technology supports high transistor density. Basically, many transistors can be put inside very small amount of space, enabling millions of or billions of transistors to be fabricated on a single chip. Now, if this is the property, right, then there is very less distance to send the data from one point to another point. If there is less distance, that means it will be more faster. So that's why we have high integration capability. So high performance. CMOS operate efficiently at high speeds, making them suitably application requiring fast processing such as microprocessor and digital signal processing. So we know CMOS is a very fast object. We can operate in at a clock frequency of gigahertz. Okay, so that's why it is very suitable for us. We can turn it on and off at very high speed. So on and off can happen, on off can happen very frequently. The CMOS will not get damaged. Okay, so that's why switching speed is very good for CMOS. Basic switching things, I hope you know. Okay, so yeah, that was basically it. And why does it if it has high density, right, then what we can do, basically while fabrication we can package them very close. while fabrication while fabrication we can package them very close. Okay, and if we package them very close, then data transfer time will have lesser amount of delay. So that is the advantage of these kind of things. I hope you have understood this point, right? So yeah, that was basically it about the CMOS transistor. Okay, so now let's discuss about technology, like few important terms I want to discuss. Okay, few important terms I want to discuss. Okay, so first is technology. What does technology mean in semiconductor? It is basically the minimum feature size. So if you remember this M2, right, here if I see somewhere, have they written it? Okay, yeah, here this they have written this, right? What is this? They're telling that it is second generation 5 nanometer technology. What does it mean? What does this 5 nanometer mean? This 5 nanometer actually means the length of the transistor. Here I have written, right, L. So L is the W by L ratio, if you remember solving the transistor, right, where L is the length of the length of the transistor, basically the channel length, correct? So this is what we mean by technology. The minimum feature size refers to the smallest physical dimension of a structure such as the transistor gate or interconnect line that can be fabricated on a semiconductor chip. It is a critical parameter that defines the capability and limitations of manufacture process. The smaller it is, the less power it will consume. That's why we are reducing it. The more density it will be. Yeah, sorry for the interruption. So as I was saying that this is what our length is. This determines the scaling of transistors, which in turn defines the performance, power and integration density. The more lower the length, channel length is, the more transistors I can fit in same area. So I will have more transistors, more processing power. So obviously we want to lower the length, but there is a limitation to it, right? We cannot reduce the length infinitely, but we are progressing. So initially we were here at 10 micrometers, around 10 micrometers here, right, around 1980s. Now we move to nanotechnology around 2000, right? So we are reducing, our length will reduce with a graph. So we are on a very fast pace. We are reducing our transistor size very fast, so it will only help us. It will give us more processing power. More transistors will be able to fit in the same area. So that's why. Okay. So like why, like I have told you, right, why integration is so much important. Previously also I have telling you that integration is very important. Why? The integration of millions or billions of transistors onto a single chip as enabled by VLSI technology has revolutionized modern electronics. Okay. So why? Because we will have more processing power, more transistors will be able to fit in the same space, obviously, then more processing power will be there. That is what is written over here. Next is less area. If I want to have the same processing power, now it will take me less area, lower amount of area, right? So if the overall area has reduced, the space will be reduced, the like power consumption will also be reduced due to that. Next is higher speed. Integration reduces the distance between the components, right? The length has reduced, so the distance between the components has reduced. The physical length has reduced, physical distance has reduced. Speed equals to distance by time. Time is same, distance has reduced. So sorry, speed equal to distance by time. Now distance, like my speed is same, speed is equals to distance by time, right? My speed is same like electron flowing speed is same. Okay, my distance has reduced, so what will happen to time? Time will also be reduced, right? Because time is distance into distance divided by speed. If the speed of electrons is same and the distance has reduced, obviously time will reduce. It will take me lesser amount of time for a data to flow from transistor 1 to transistor 2. So definitely that will be only helpful to me. Okay, that's why the third point, higher speed. Okay, and portability. The smaller the device is, the easier I can port a like I can take that device in some other place, in some other areas. Okay, that's why the term portability is here. Next is smaller integrated systems enable the development of lightweight and portable devices. Okay, like that is the point. Improve reliability. Integration reduces the number of interconnections, like uh, to the outside source. Okay, if there is a failure in the outside source, then the reliability will be reduced. But as the number of integrations has been reduced, because multiple chips will be inside the same structure only, so it will be more and more reliable. Okay. So this here, right, one thing I forgot to mention, well, low power consumption, obviously you understand, because of course less area, low power consumption. Why? Because there will be less cable loss. Why less cable loss? Because to interconnect each transistor, right, I have to connect them with cables. If the cable length has reduced, obviously the distance for the electrons to travel has reduced, so the loss will also be reduced, as mentioned here. Shorter interconnect distance and optimized power management. Okay, so like these are the few points that you should know. Okay, so okay, one few topics have been repeated here. These, okay, these are have been repeated. I need to delete these things. Repeated twice. Okay, here I am. So now a few more important points. Although this is not that important, this will not be asked in interview, but you should know the whole flow. Like basic idea you should have. Like how does a VLSI process happen? Because sometimes in interview the interviewer can ask. If you know, don't tell them by hand you know this. If they ask, then you can start talking about it, that I have studied a bit about this. Okay, so I will discuss about the design flow. Just overview. I'll give you an overview. What is a ASIC design flow? ASIC design flow is application specific integrated circuit design flow. Okay, it is a structured process to develop a custom chip for a specific application. So what is a design flow to develop a chip? That is what I am discussing. So this is the overview. First, we have a design spec, right? How fast you want your ADC, okay? What is the clock frequency? What is the INL, DNL? What is the accuracy? How much SNR you want? SNR means noise, signal to noise ratio. How much performance you want? How much speed you want? Okay? How much data you should be able to store on that particular chip? All those things will be here decided from the design specifications. Designers will decide this, right? Once designer decide a specific, then they go to the behavioral description. Basically they will not directly go into the coding, they will first understand in the higher level how they can design that. That is what written over here. Design specification, like functionality, signal processing, control logic, speed, power, and obviously they will decide which technology they want to use. 5 nanometer technology, 7 nanometer technology, like that. Constraints, like obviously this is very important constraint, like budget. How much money they have to build the chip, right? How much should it cost? Because they have to sell it out to the customers. So customer, like they have to build a chip such that the customer should be enticed by that chip price to performance ratio, manufacturing timelines, how fast I want that. So all these things, right? All these things. Okay, number of how many inputs it should have, how many outputs it should have. Okay, power, all those things I've discussed like that, right? So this is all what design team, this is not just the design team which decide. Design team talks with the customers, with their desired customers as well, what the customers want. According to those customers, they will say, hey, I want a high speed ADC, something like that. So customers will say. So first they decide how my product should be. This is what the designers decide. Okay, they discuss back and forth with the customer, then they come to a specification, they write down the specification. Next is they come to the this behavioral description. What is this behavioral description? This is known as the architecturing. Architecturing is develop a high level architecture to meet the design specification. Like this is a common microprocessor architecture, right? So what in architecturing, what do they do? They divide the bigger problems into smaller ones, just similar. Let's say I have to design a 4:1 mux. What I will say is, I don't know how to design a 4:1 mux, but I know how to design a 2:1 mux. So I will design two 2:1 mux and then interconnect those, because I hope you know that you can design a 4:1 mux with two 2:1 mux. Okay, so dividing our bigger problems to smaller one. So the partitioning the system into modules. Like I will divide the responsibilities. You decide the control unit. You decide the GPU. You decide the CPU. Of course, a single person cannot decide, right? Partitioning the like the responsibilities. Basically, for a M2 chip, there is a GPU, there is a CPU, there is a RAM, there is a there are other things as well, right? Like memory, storage, all those things. So I have partitioned the responsibilities, and now I will develop modules for CPU, module for GPU. Then they will be reusable. Why we want to make modules? Because modules are reusable, and this I will come to later on. Why reusability is very important? Because once you have built a module, right, when the next person will come and work, like he or she will design a CPU, he can directly start with the previous module. Of course, we need to make a few changes because the specs of the new chip will be different, but the changes will not be that much drastic. Okay, the changes will not be that much drastic. We can use the modules. Okay, now defining data flow and control flow, like how the data will flow from the input to output. All those things will be defined in the behavioral model. Selecting algorithms and hardware software trade-offs. As I told you, right? If I can build a mux 4:1 mux in many ways. One of the ways is 2:1 mux. Okay, so I have selected 2:1 mux as a hardware for the 4:1 mux. Okay, you can design something else as well. You can decide something else as well. Okay, so all these things will be decided in the architectural, that is here in the behavioral description. Now I will come to the RTL coding. In RTL coding, what we do? We implement the design at the register transistor level using hardware description languages like Verilog or VHDL. Okay, so this is a RTL code. Basically, this is a Verilog code. Whatever we have decided in the behavioral level, we code it in RTL level. Okay, to describe them in individual modules, we define the data path, control sequence, clock domain, and we ensure the modularity and readability of the code. Okay, we code it. Now after coding, right, this code, then our Verilog converts this code into hardware. But of course, what we do is, once we code this, right, in hardware, then we come to the verification. We verify the RTL functionality. That is the fourth point. We verify the RTL functionality. So objective is to ensure that the RTL design meets the specifications through simulation and testing. What does it include? It includes like functional verification, code coverage, formal verification. So what are these? Basically, we also have few tools for this. We have few tools. What are those tools? Those tools are System Verilog. Verilog is what? It converts the RTL code into hardware. Now System Verilog is what? System Verilog is used for verification. Whatever we have coded, are those correct or not? Basically, let's say I have coded a high speed ADC. So I have designed it for SNR of 30 dBs. So when I am verifying it, whether the SNR is 30 dBs or not, or is it is higher than that, so that means whatever I have designed, that is not good enough, I have to design something else. So that's why you can see there is a loop back here. RTL functional verified. I'll verify. If it is not matching with my design specs, then again I will come to the behavioral description. If it is not matching with my current specs, or RTL description, whichever one is wrong, whichever step I was wrong, I will rewrite that step. Okay, that's why there is a loop back here. If it is verified, then I can directly go to RTL to logic. Okay, RTL to logic synthesis, I will explain about that. So there are few tools like system verilog, then obviously there are simulation tools, right? What are the simulation tools? Simulation tools like MATLAB. Okay, I was just checking the sound, whether there is some noise or not. So we can use these tools. First, there is known as functional verification. What does functional verification measure? It verifies the logic correctness using test benches. Okay, using test benches is verifies the logic correctness. So basically any bugs we have in the code, in the logic, that it will verify. Functional means functionality is wrong, like it is supposed to be a ADC, analog to digital converter, but it is not properly working. That means the functionality is wrong. Next is code coverage. Ensure all design paths are tested. Like in the circuit at hardware, all the paths should be tested. There are many processes that like different companies use to ensure there is proper code coverage, that whatever hardware I have made, all the paths, all those paths should be tested. Even if one of the path is wrong, right, then ultimately at the final uh, uh, what do you say, production of the chip, something will go wrong. Okay, then there is formal verification. Mathematically prove design correctness and against the specification. Okay, this doesn't check the spec mates, this checks the functionality. If I have designed a mux, then it should be able to select any 4 lines, correct? I don't check how is the strength of the signal or all of that. All that is checked in the formal verification. After like functionality is checked, right, then we check like whether the spec is getting met or not. Basically the output SNR, how is the output SNR, how is the uh, what do you say, how is the INL, how is the DNL, all those things. After that, after this happens, right, then we'll go to this synthesis, this whole step, right, this whole thing is also known as HDL design synthesis. This portion is known as HDL design capture. We design it, we put in the schematic entry, all those things, but we actually not convert it into hardware, just design capture. Now we are synthesizing it to it hardware. That's why it is known as HDL design synthesis. Okay. So here we synthesize, convert the RTL code into gate level netlist using synthesis tools like Verilog and other things. Map the high level RTL constructs using the technology specific logic gates. In your synthesizing tool, there will be few specific things, right? Okay. So that is what it will map. Optimize for power and area performance, generate reports to validate the timing and resource allocation and utilization. All those things it will do. Just don't have to go too much in depth of this. Just try to understand the steps. Okay, just try to understand the steps. Okay, so actually this part 1 is common for most synthesis. Okay, so basically this, right, I will write here. So steps, this HDL, like for most cases this first step is always common, but this last few steps, right, implementation, this can be a bit different, so I will not discuss about this currently. So we write here that design this design capture or design flow is almost same. Design capture is similar steps in design capture. Almost similar in everywhere. Okay, but from synthesis onwards, the steps will change. Okay, that's why I will not discuss about those steps, right? I will ignore those steps for now, because just I wanted to give you a basic overview. That's it, nothing else, just a basic overview. Okay, so like this is what a HDL design synthesis tool does. Because if I have a code, right, like this, I will not explain you what this code is, I also don't know. Just basically what it does, HDL code converts this code into hardware. Okay, I will just zoom it out. It will just convert this code into a hardware. Now there will be some inputs, right? This is the input, let's say this is the input. These are all the inputs, these are all the inputs, and outputs, like here there will be output as well. Okay, don't have to worry about this code, we'll understand this code. And the interconnections, right, is decided by this code. This interconnections are also known as data path. Okay, so in the Verilog code I will give it some inputs. Code will be given some inputs. Okay, inputs like the synthesis, not the Verilog code, sorry, the synthesis tool. What inputs I will give to the synthesis tool? After giving it this code, I will give it some constraint that the power must be less than 100 watts, something like that. Okay, the speed must be more than this, clock frequency must be this. Okay, give it some constraint. Of course I will give it the RTL code. I'm talking about the synthesis tools. Synthesis tools. So what are these constraints? These constraints are used to optimize for what I want to design. Optimize for, like, let's say area. My area must be this, speed, power, and more. Okay, then RTL code, of course I will give. Then there is standard cell library. In the synthesis tool there will be some standard cell library, or I can give my own library that use these type of NAND gate which has delay of 1 nanosecond. If the synthesis tool has some like if the synthesis tool has some kind of like, what do you say, some kind of NAND gate, but it has 5 nanosecond delay, I don't want to use that. Okay, I don't want to use that. So I will give it some standard cell library as well, which have all the information of what? It has information of the logic gates, which of course it will implement on all few other hardwares, few standard hardwares. Okay, so that is what the synthesis tool will do. So there are many synthesis tools like Synopsys uses or something. Okay, they convert this, so I will not discuss about that right now. So finally in the output, right, what I will get in the output, I will get a net list from the synthesis tool and what kind of hardware it has to use. This is the output, this is the output, and the input, of course I have told you this I will give. And in the output as well they will show me the data path and all those things. Okay, so that is what a synthesizing tool does. Then after this, like, this is also a very important step for designing a chip, known as design for testability, DFT. This is not that signals and systems topic, DFT, right? This is design for testability. So DFT, the objective is to incorporate testing features into the design to ensure manufacturability and detect defects. Because functionality you have checked, okay, all those things you have checked, but now once you try to manufacture, there can be some manufacturing defects, some problems will be there. Okay, so basically, right, this DFT is a very sought after job, because this checking this, right, is very difficult. You have to minimize the processing time. Let's say somewhere in your design you are using a 3 input NAND gate, 3 input NAND gate or AND gate, whatever you want to say. You're using a 3 input AND gate. Now how many inputs I need to give to check this 3 input NAND gate manufacturer defect? Like, I have to check every single hardware in DFT, right? Every single hardware. How many inputs? How many total combinations? 0, 1. So 2 raised to power 3 combinations I need to give to this AND gate and check the outputs. So total I need to check 8 different cases. 8 different cases. Now can I somehow minimize this? Can I somehow minimize this? So that is the task of a DFT engineer. Okay, to check this properly. Can I somehow minimize this? Okay, so we have to design a test plan so that I can minimize this. Like, you have to define a logic. So I will not go into that right now, but you have to design a logic. Now 8 different cases is fine, but let's say I have a chip that has 1000 inputs and I have to check all the 1000 inputs. So how many different cases I will have? It will be 2 raised to 1000, which will be a lot. Okay, so I don't want that, right? Of course chip can have 1000 inputs, right? It has 1000 registers. I have to check all of them. Even if one of them is wrong, that means what? My chip is not working properly, it is not functioning properly, so I have to discard that chip. So that's why designing this kind of functionality is very, very important. Okay, so there can be process defects. Like, if you are designing in some particular technology, there can be few problems with that, so you will not use that. Okay, there can be some open circuit, short circuit fault in your path. Okay, so you have to add additional hardware to check defects. So you have to add this additional hardware to check defects. So there should be built-in self-test or some scans. I will not go too much in depth here, just giving you an idea so that you understand what is the job of a VLSI engineer. There are many things in VLSI, right? Not just simple electronics. Okay, developing analog chips, not that. Okay, there are many things. So all these things are there. I will not go too much in depth. Then you have your timing analysis, also known as STA, right? So this is where you decide your clock frequency is correct or not. Okay, so in all these steps, right, you go back and forth. If you see this particular thing, right, you go back and forth to your initial step, right? Why? Because you have to discuss with the designer as well. Hey, we did some DFT test, this is not actually what we are getting. We are not getting our desired performance according to your design, so we may have to change few things. Okay, so this is like very basic thing. I hope you know what is like setup time, hold time. You have to do check whether there is no STA violation or not, all those things. Okay, you have to verify clock domain crossing CDC for multiple clock designs. If I have multiple clocks, are they synchronized or not properly? So all these things you have to design. So this, right, is for layout, guys. So I will not discuss much about these things. This is after all these things have been done, right? Finally, functionality have been checked, design has been checked, testing has been done. Now you come to the layout part, where you actually start the layout of the chip, which will then go to the manufacturing. Okay, all these things you go back and forth between layout, placement. Okay, because there can be many optimizations, right? If you place the chip just before here, just before this particular position here. Okay, there can be many things. I will not discuss about that. A few basic thumb rule there are, like DRC. DRC is what? DRC is design rule check. Just like a handbook, that if you are using this technology, then you must place the chips like this or like this. Okay, so design rule check. So few basic things you have, that's it. Okay, next is their formal verification, power estimation. I will not discuss like this, right? All these steps are going back and forth, something like that. You can discuss with your designer back and forth. So I have given you a basic overview about the design flow. Not that important, but still to get a good idea, because in interview sometimes they may ask you design flow. You may not know everything because you are on BTech level. That's why I gave you overview. Now let's discuss about hardware descriptive languages. Why are they needed? Okay, so for years, programming languages like Fortran, Pascal, C were primarily used for sequential programs. What is sequential program? Sequential program means sequential execution of programs. Sequential execution. What do I mean by sequential execution? So in sequential execution, let's say I have this code, right? A plus B, like C is equals to A plus B, E is equals to D plus F. In sequential program, this will happen first, then this will happen. Like, let's take an example for C, right? In C, this will, like, this line will be executed first, then this line. But what we needed, similarly in the field of digital design, there was a growing demand for standardized language to describe the digital circuits. What were those digital circuits? Like because digital circuits, what they used to do, they used to work concurrently. So this led the development of HDLs, also known as hardware description languages, which enable designers to model the concurrent processes inherent in the hardware system. So if the same code is written in Verilog or a HDL, right, hardware descriptive language, D plus F, then what it will do, both of this will happen parallelly, because I will have a adder, two adders I will have, okay, two adders I will have, input will be AB, here input will be DF, this will be the output, this will be C, this will be F, this will be E, okay. So this, right, this is not like this will happen first or this will happen first. I have separate hardware for this, so they will happen concurrently. So there is a huge difference between normal C language and your Verilog. So don't get confused. Your hardware descriptive language, right, HDLs, are happen on parallel execution, okay. They don't happen sequentially, they happen parallelly. Two of the most prominent HDLs are Verilog HDL and VHDL, which gained popularity. We will study Verilog HDL. Verilog HDL was introduced by Gateway Design Automation. VHDL was developed by DARPA, Defense Advanced Research Project SSC. So this is not important, this is important, okay. So yeah, that is about that like Verilog HDL. So initially, while HDMs became widely adopted for logical verification, designers still had to manually convert the HDL based design into schematic, basically the synthesis, right, showing gate interconnections. They have to manually interconnect. This process changed dramatically with advent of logic synthesis in late 1980s. Designers could now describe circuits at the register transistor level, okay. Basically they can define at the register transistor level using HDL. Then there will be some like synthesis tools. So RTL focuses on the how data flows between registers, like this, right? AB is here, how is data flowing through a full adder, then I'm getting the output like this. RTL focuses on this, and how the system processes the data. How does it process? There I have a adder, sometimes I will have a subtractor, then I will have a multiplier, something like that, okay. Then logic synthesis tools automatically generate the necessary gate level details. Like here, right, I have only written this is a full adder. Inside this full adder, what type of logic gates are there, AND gate, OR gate, I don't care. Logic synthesis tool will automatically generate the gate level details, okay, and interconnections from RTL description. Whatever description I have given here, it will automatically do that. I will say I have a full adder, it will automatically inside the full adder, it will understand what kind of gate level things it has to do, okay. That is what the logic synthesis tools do, okay. Instead of manually placing gates, designer could focus on high level functionality like the logic and all those things, and the manual thing will be automated, leaving the detailed implementation to the synthesis tool. Synthesis tool will be automatically do the detailed implementation. So what is the role of Verilog? Verilog is used to write, like we can write, we can define our circuits, all those things in Verilog code. We can simulate the functionality. We can synthesize into gate level netlist by using synthesis tool. Also we can perform placement and routing, which we don't do, but we can perform this as well, and we can validate and test using physical implementation as well. So these are all the design flow. Like this is what is the role of Verilog in the design flow, right? It is used here in these things, in these three things. In these three things, Verilog is used. The last two things can also be done, but we generally avoid doing that. We do it with some other tools, okay. Advantages of Verilog: concise and efficient for large design, support for behavioral structure. We'll understand what is behavioral structure, what is like gate level modeling, structural level modeling. We'll understand that, don't worry about it. Then there is strong integration between the EDA tools. EDA, which I told you, is the design automation tool, right? So it has integration with those EDA tools as well, okay. So that's it basically for this lecture. This lecture was mainly theoretical. We did not do any coding or something, because I want to get a good foundation. Why are we doing what we are doing, okay? Then obviously we'll understand the code, and from the next lecture onwards we'll understand about the different design methodologies in Verilog. Also we'll implement a half adder with the different levels of abstractions, okay. Thank you for watching, and I hope to see you in the next lecture. Until then, happy learning.